Hey guys, in this video we're going to go through some proofs by contradiction which involve trigonometry. We have a couple of examples that we're going to work on. The first one being proof by contradiction that for every x in between pi over 2 and pi, sine of x minus cosine of x is greater than or equal to 1. That's exercise number 1. And exercise number 2, which is quite interesting by the way, is to prove by contradiction that the tangent of 1 degree is an irrational number. And we're going to go through these two exercises following the 5-step process, which involve, number 1, writing the proposition, which means what we're trying to prove. The proposition, for example, for exercise number 1 is for every x in pi over 2 to pi, in the interval from pi over 2 to pi, sine of x minus cosine of x is greater than or equal to 1. Then step number 2, which is to negate p and assume that the negation is true for the sake of contradiction. Number 3, we're going to develop the exercise algebraically. Number 4, after we get some nonsense, something that is simply wrong, we state that's exactly where the contradiction lies. And number 5, we write the conclusion. So let's get to it, starting with exercise number 1. So again, we're going to start exercise number 1, writing the proposition. What is the proposition P? For every x value which lies in between pi over 2 and pi, including pi over 2 and pi, sine of x minus cosine of x is greater than or equal to 1. We are going to assume, for the sake of contradiction, that not p, and of course you have to write what not p is true. And in this case, not p means that for x values in this interval, sine of x minus cosine of x is less than 1. First things first, let's analyze what is this interval. What quadrant are we talking about? Now this is the second quadrant. And in this second quadrant, the cosine is negative and the sine is positive. Remember that you read sine in the vertical axis and cosine in the horizontal one. So for every angle x over here, we have a sine of x greater than 0 and a cosine of x smaller than 0, which means that sine of x minus cosine of x is a positive number. Now, why am I saying that? I'm saying that because if we square both sides of this inequality, the inequality will not flip. We don't need to worry about it. So let's square both sides so we can simplify something. So what we have is sine squared of x minus 2 times sine of x cosine of x plus cosine squared of x less than 1. 1 squared is just 1. Now, knowing that sine squared of x plus cosine squared of x is equal to 1. And at this point, you probably realize that in order to tackle proofs by contradiction which involve trigonometry, you got to be familiar with trig identities. We can replace this sine squared plus cosine squared by 1. So we have 1 minus 2 sine of x cosine of x less than 1, which means that negative 2 sine of x cosine of x will be less than 0. Now, I did mention that you don't need to worry about flipping the inequality, but that was for the first step, which was to square both sides. If we want to multiply or to divide this inequality right now by a negative number, we do, of course, need to worry about it. Now, multiplying this whole thing by negative 1 will give us 2 sine of x cosine of x, not less than, but greater than 0. And again, we flip the inequality because we're multiplying by a negative number. Now, what is 2 sine of x cosine of x? Again, using a trig identity, this is the same as sine of 2x, which means that what we have here is sine of 2x greater than 0. Now, let's check if this is actually the case. Maybe the contradiction lies right here. We know that x is varying between pi over 2 and pi, including pi over 2 and pi. Now, if x ranges from pi over 2 to pi, that means that 2x varies between pi and 2 pi. The only thing that we did here was to multiply all of these terms by 2, which means that 2x lies in between pi and 2 pi, including pi and 2 pi. Now, we're talking right now about quadrants 3 and 4. The angle ranging between pi and 2 pi, that's where quadrants 3 and 4, what they are. Now, let me color code this region differently so we can paint it in our diagram. Now, do notice that in between pi and 2 pi, the sign is either negative, which is for every possible value except for 2, which is exactly pi and exactly 2 pi. So sine of 2x is either 0 or negative. And what we're saying here is that sine of 2x is positive, which is a contradiction. And that's exactly what you have to state in your conclusion, which is a contradiction, given that from pi to 2 pi, sine is either negative or 0. And do state that we got these numbers pi and 2 pi because of this. So notice that if pi over 2 is less than or equal to x, which is less than or equal to pi, then pi is less than or equal to 2x, which is less than or equal to 2 pi. And lastly, therefore, by contradiction, p is true. And if you stated p before, as we did over here, then you don't need to rewrite p. Now let's move to the second and most interesting exercise. Now moving to exercise number 2, prove that tangent of 1 degree is an irrational number by contradiction. Now what is the proposition here? The proposition, which is what we're trying to prove, is tangent of 1 degree is an irrational number. Now we are going to assume, for the sake of contradiction, that not p is true. In other words, tangent of 1 degree is not an irrational number, which means it is a rational number. And how do we represent rational numbers? We represent them by a quotient between a and b, or p and q, whatever you prefer, where both p and q are integers, and p over q is an irreducible fraction. Now, this is the part that usually students get stuck. What should I do here, right? And the next step, although not trivial, is quite interesting. We're going to, by applying the following identity, tan of a plus b being equal to tan of a plus tan of b over 1 minus tan of a times tan of b, replace both a and b by 1 degree, which means that we have, when applying this identity, tangent of 1 plus 1, which is just tangent of 2 degrees, equal to tan of 1 plus tan of 1 again over 1 minus tan of 1 degree times the tangent of 1 degree as well. So we have on the left tangent of 2 degrees equal to tan of 1 plus tan of 1 over 1 minus tan of 1 times tan of 1 again. Now we did assume that tangent of 1 degree is a rational number, so let's substitute tan of 1 by p over q. However, we can already affirm that if tangent of 1 is rational, well, then tangent of 2 is a rational number as well, due to the fact that we have a rational number here, which shows up over here as well. And the sum of 2 rational numbers is a rational number over 1 minus the product of 2 rational numbers. The product themselves, or the product itself, is rational. 1 minus a rational number is rational. And if you take this rational number over this rational number, you still get a rational number. But let's also get there by replacing tan of 1 degree by p over q, just this time. So tangent of 2 degrees is p over q plus p over q over 1 minus p over q squared. So we get 2p over q over 1 minus p squared over q squared. Now the algebraic process here does take a few steps, so that's why we're only going to do it this time. Now we have in the denominator q squared minus p squared over q squared, and in the numerator 2p over q. So we have 2p over q times q squared over q squared minus p squared. We can simplify these q's and we get 2pq over q squared minus p squared. But as I mentioned before, we already knew that this manipulation of rational numbers would lead to a rational number, and that's exactly what we're going to state in the next few steps, so this doesn't become boring. Okay, now what's the conclusion here? Therefore, if tan of 1 degree is rational, then tan of 2 degrees is also rational. Now that's an important conclusion, because this iterative process will lead us to get some sort of nonsense down the road, okay, in a few steps. The next thing that we're going to do is to find tangents of 3 degrees using a similar strategy. Now let a be 2 degrees and b be equal to 1 degree. Now what is tan of 2 degrees plus 1 degree, which is tan of a plus b? That is tangent of 2 degrees plus tangent of 1 degree over 1 minus tan of 2 degrees times tangent of 1 degree. Now, knowing that all of these tangents, these are rational numbers, or at least we're assuming that they're rational numbers, we actually assume that the tangent of 1 degree is a rational number and tangent of 2 degrees as a consequence was also a rational number. Given that we're manipulating these rational numbers, the result itself, which is the tangent of 3 degrees, will also be a rational number. So if tan of 1 degrees or 1 degree and tangent of 2 degrees are rational numbers, then as a consequence of that, tangent of 3 degrees will also be a rational number. Now you probably see where we're going with this. By applying this process multiple times, and what would be the next step? To call A 3 degrees and B 1 degree, and then A 4 degrees and B 1 degree, and these would allow us to find, for example, tangent of 4 degrees, tangent of 5 degrees, and so on. We will get eventually a tangent of 30 degrees. We will get to 30 represented as a rational number, which is not true. What is tangent of 30 degrees? Tangent of 30 is, you can represent it as 1 over root 3 or root 3 over 3, which is a contradiction. So here lies the contradiction. And then concluding by contradiction, we can state that the proposition P is true. What is P? P is the following proposition. Tangent of 1 degree is an irrational number. So we just proved by contradiction that tangent of 1 degree is an irrational number.